going to continue on with Unit 2.5, the periodic table, today, and kind of get into the more of the how did those really long numbers come to be, or how are they calculated? The atomic and molecular masses are, and this is where sometimes chemistry can be a little difficult, is that we have a number of different terms that we use for atomic mass. So it can be atomic mass or molecular mass. And it doesn't matter which one it is, they are both essentially like the same thing. They are just a little bit different, but a lot of times we use them interchangeably. So the two terms are used interchangeably. And we can make this measurement using what is called a mass spectrometer. Now, I can tell you that we do not have a mass spectrometer in my classroom, but I have been fortunate enough to use a mass spectrometer before. And it is kind of fun, and in a way, I always find it a very interesting idea of what you're actually doing. Okay, when you think about what you're actually doing, and this is obviously a simple version of it, and you would take a sample, you would make a sample, and then you would add it to the plate. It would heat up. It would go through a number of kind of filters to kind of focus everything in, so that when you move the magnet to try and get where are you getting peaks at is what you would find. And you would find certain peaks for chlorine and at a certain there, and you would see you would be missing something. And so it would have a little bit of a miss, and so you would have to turn and change it just a little bit to get in the chlorine 37 ions and get those to be present. So that's pretty much where these numbers are coming from. It is something that for those of you that go on to bigger and better things, you might actually get to use one of these. It is seen in many colleges and universities, and being able to use these. So this is where all those numbers are coming from. So that's how they know. We use large amounts of molecules. We can't actually detect one or something else. Not only that, the atomic masses are actually very small numbers. Okay? Those numbers are small, and therefore we have to ramp them up. And so when we actually look at, say, the atomic mass of, say, like hydrogen, should actually be somewhere on the order of 1.001 times 10 to the negative 25th, I believe, grams. That's an extremely small number. Hard to actually make out that, and if anything, I would think very difficult to make calculations involving. So what AMU does is the AMU of hydrogen brings it to a much more normal number of, say, just a 1.001. And the label for average atomic mass, as it's there, AMU, it is just that, AMU. Now, these are a weighted average. Okay, It is a weighted average that we find. Their abundance in nature. Okay, their abundance in nature. Now, I'm not a super big fan of AMUs. At this point in time in what we're doing, they serve its purpose and that's about it. Later on, in say Unit 4, we will move that over and actually call it and have a different label of grams per mole, and that's more of what's called the molar mass. For us at this point in time, we're not going to be worried about the molar mass. The molar mass is just another term for atomic mass or molecular mass that deals more with the mole. Okay? That becomes very helpful later on. However, it's just something there. But for now, AMUs are the route to take. Okay? And again, they're a weighted average based on their relative abundance. So how do we do a weighted average? Well, just like in math class, you would be asked to do a weighted average on how to do some of these. And we'll go through the steps. I'll kind of shrink the screen down and we'll go through the steps of how to calculate out the average atomic mass of, say, chlorine. Now, a lot of us will look at it and say, well, why don't I just look on the periodic table? Well, yeah, we can do that now, but there's no guarantee that, say, in your problems, in your homework, or your problems, say, on a test, that you're going to actually have that ability. They might say a naturally occurring element has these things. What element is it? Or here's a hypothetical element. What is the average atomic mass for it? And so those are kind of where you're going to, why do you need to kind of go through the steps and not just always use your periodic table? And so we're going to be able to check ourselves and kind of go from there. And as we can see, the chlorine 35 does not actually have a mass of 35. It actually rounds up to 35. And the same thing with chlorine 37, actually rounds up to that as well. So let's resize this so I can have plenty of workspace. And so from here, we will say that I have chlorine 35 is 75.78%. No, I can't really do much with that, but if I divide it by 100, I would then have .7578. Now I would need to do the same thing for the 24.22 to get the 0.2422. Now this is a step that many students are able to do in their head, kind of converting a number from the percentage into its decimal varying. Because many of you, if you calculated, say, your grade on a test and you put it in your calculator and you saw 0.7578, you would very quickly and able to move the decimal place 2 places and say that you got a 75.8 or 75.78 for that. So that's a step a lot of times we are going to skip because it just happens so naturally and with that. So when I set these up, that's where I'm going to take those numbers from. And so I'm going to take my 0.7578 and I'm going to multiply it by the mass of chlorine 35. Okay, so I'm going to take that and multiply. And then I'm going to do the same thing for the other one. Now, I set mine up in this manner because I find it keeps things nice, neat, and organized. That does not mean you have to do it that way. You need to figure out the method that you are going to use that will make you successful. Now, here comes the why I do it this way, is because when I take my handy dandy calculator and I multiply 0.7578 times 34.969, I get an answer of 26.499. We'll say 95. We'll go 4 decimal places. My other one, I take my handy dandy calculator, multiplied 0.2422 times 36.966 to get an answer of 8.9531. We'll go 32 on that since it would round up. Okay. So from here, though, I'm able to add them up. And that's why I kind of organize them this manner. And so now I can do the addition that I need to do. Now, can you do the addition longhand as I'm doing? Yes. Can you do the addition using a calculator? Yes. Whatever method works for you will be probably the one to go with on there. But I like to keep myself on my toes and be able to do long, kind of longer addition problems. So that is my answer. Now, if I look on my periodic table, I have an answer of 35.4527. Well, looky there. That's exactly what we got. So that means we got the problem correct. Excellent. That's what we want. So let's think about this one. There's 2 isotopes of bromine, bromine 79 and bromine 81. Based on the average atomic mass of bromine, which is, I believe, 79.9, so very close to 80, the distribution is one that we can't really calculate. Now, we don't have in this question the numbers that bromine 79 actually is. Is it 79.5? Is it 79.1? Is it actually 78 point whatever? And we don't know what bromine 81 is either. And so we have to kind of guess. Now, we can be close and say almost 100%, but here's a real quick thing that we can do. If we take 50% and multiply that by 79 and add that to 50% of 81, we would, and then add those two together, we would find that our answer is 80, which the atomic mass of bromine is 79.9. So here is and it's like you're guessing on which one is which, but we can actually kind of look at it real quickly by just looking at one of that. Now, if that came out to be some other weird answer, we would then have to try to eliminate answers. So this is a little bit more of a thought-provoking question that is there. Something you might see probably more like in your homework or on a weekly quiz. So let's look at another example of this. Naturally occurring silicon is 92.23% silicon-28, which actually has an atomic mass of 27.97693, 4.68 silicon-29, and 3.09% silicon-30. And then calculate the average atomic mass of silicon. So, let's try it out. I'm going to kind of skip over the dividing by 100 step and go straight into, I'm going to go kind of write it in a little bit different of a method and say that it's silicon-28 there. And so I'll keep all my numbers together, and you can see maybe a different method of how I organize some of that. And let's go 27. Three. Let's do silicon-29 is, and here's a big one that I see a lot of students making mistakes on, is not putting that 0 in front of the 4 instead of just putting it as 4.468. But that would mean that it was 46%. So this is one of the reasons why I have my students always show their work, so that if you do make a math mistake, such as that, it's not overly detrimental to your grade on the test, so that you can, well, kind of still have, it's like, why did you get that question wrong? Well, because you did that part. And then silicon-30 is, again, don't make that mistake. Ooh, nobody called me out. How come? I wrote the percentage of silicon wrong. There we go. Put all of those into my handy dandy calculator. And 0.309 times. Give a value of pretty small, 0.926. We'll go 2 on that. Next one, and that would be a value of 1.3561. And lastly, having the value of 25.8031. Add all those up. And we double check to see if we did it right by looking for silicon on the periodic table, and it's 28.0855554. I'm pretty happy with that, as AMU.